Hey guys, welcome back. Today's lesson is on Newton's law of universal gravitation. His law states that objects attract each other with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. His law is backed up by this mathematical formula here, where F is the force of attraction between any two bodies, such as the Earth and its moon. Newton came up with a gravitational constant, which is represented by capital G, not to be confused with little g. So F is for force in newtons. And then G is the gravitational constant, which is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. We're going to multiply that constant by the two masses, such as the Earth and the Moon. So mass 1 and mass 2 are any two masses in kilograms. And then r is the radius or the distance between them. The reason it's r is because one of these objects is generally going to circle the other object, such as in this case, the Moon circles the Earth. And this will be the radius in meters. We can put the Earth as our center point here, and just to show this, the force of attraction between the Moon and the Earth is due to their two masses and the distance between them squared. A satellite is any celestial body or man-made object that orbits a larger body. So the Moon is a satellite of the Earth. Earth and the other 7 planets are satellites of our Sun. The Hubble telescope is a man-made satellite of Earth. There were others. The first one was Sputnik in 1957, launched by the Soviet Union in the Great Space Race. The United States was, I should say, slightly less, they were a bit disappointed, let's put it that way, that they did not win in the Great Space Race. The purpose of Sputnik here was just to prove that you could launch an object into orbit around Earth, and they gave it a second purpose to collect some atmospheric data. So understanding Newton's law of universal gravitation is very important and is practical in today's technological world. Let's put it to use. I'll do an example where we will calculate the gravitational force between two students in class. Now, the gravitational force is universal. It is infinite. That means it doesn't matter if the object 1 is here on Earth and object 2 is off in another galaxy. They still experience a gravitational force towards each other. It's just that the Earth here is the largest mass closest to us, so that's going to create the most pull that we experience. And you're not going to feel the effects of other bodies such as the Moon or the Sun. But the distance that gravity acts is infinite. So here we're going to take our formula and substitute. We have student 1 with a mass of 65 kilograms. First we'll put in G, 6.67 E negative 11 Newton meter squared per kilogram squared. Mass 1 is 65 kilograms times mass 2, which is 102 kilograms. Now we're going to divide this by the distance between the two students squared. The distance between them is 2 meters. Now we square both the 2 and the m. I'm going to calculate my numerator first. I'm getting 4.4 e negative 7, and then I'm going to divide by 2 squared. And we get 1.1 e negative 7 newtons. So you can see that that is a very, very small number, and that's why you won't experience as much of a gravitational force as you would like to actually say that this actually occurs, but it does occur. Let's try another one. How far apart are two stars of identical mass if the force between them is 1.9 e24 newtons? So the force now is 1.94 e24 newtons. We're going to set that equal to the gravitational constant. Times identical masses, so 3.01 e30 kilograms. Now if I multiply it by that again, I'm going to run off the page if I write that out. So this means I can just square it, because anything times itself is itself squared. And we're going to divide by the distance between them, which we don't know. We want to know how far apart they are. To isolate r, we're going to move this over. So multiply by r squared. And we get r squared equals, I'm going to take this 1.94 e24 newtons. I'm going to divide it over here. So we have 6.67 e negative 11 times 3.01 e30 kilograms squared divided by 1.94 e24 newtons. And then we'll take the square root of our answer. All right, numerator divided by the denominator, 1.94 e24. And now I'm going to go ahead and take the square root of that answer. And I get 1.76 e13, and the radius is going to be in meters. Aside from Newton's law of universal gravitation, we can derive some other equations from Newton's second law, force equals mass times acceleration. Let's derive an equation that will calculate the orbital period of a satellite starting from Newton's second law and incorporating centripetal acceleration. So we're going to substitute for A. Centripetal acceleration is 4 pi squared r over t squared. This is where I'm going to get the time period from of my satellite. And now I'm going to replace force with Newton's law of universal gravitation. G m1 times m2 divided by the radius between them squared equals m times 4 pi squared r over t squared. Next, we're just going to rearrange this. I'm going to cross multiply, bring that t squared over. I'm going to bring this r squared over. And then I'm going to go ahead and divide by the gm1, m2. So on this side now I'm left with t squared equals m times 4 pi squared r times r squared divided by g m1 m2. Now we need to do some canceling and some simplifying. We're going to take one of these m's and cancel them out. We're going to take these two r's and combine them to get r cubed. Now we have t squared equals 4 pi squared r cubed over g m. And I only have one mass now, so I don't need to put the subscript 2. This is going to help me find the time period of a satellite that orbits a certain mass, whether that's the moon orbiting Earth or the Earth orbiting the sun. We can get a lot of data from this. So now we'll take t and square root the other side of the equation. Square root of 4 pi squared r cubed over gm. We're going to extract some of these squareds here to give us 2 pi times the square root of r cubed over gm. So now we have an equation to find the time period of a satellite orbiting a larger body, such as the mass of the sun here. S represents sun, but it could be any larger mass that any smaller satellite is orbiting. Let's do one more. Let's say that we want to find the speed of a satellite. And we can also derive this from Newton's second law. We're going to start with F equals ma. Instead of a, we're going to replace this with centripetal acceleration where we have v in it, which is v squared over r. Carry down m, carry down f. Now I'm going to replace F with Newton's law of universal gravitation. Now we'll rearrange and simplify. Take the r squared and multiply it over here. Actually, let's do this the other way. Let's take this r and multiply it over here so that we can isolate v. Okay, one of these r's will cancel out. I can divide by m on both sides and cancel that out. So I still have this r here. I got rid of that m, and I'm going to be left with v squared on the other side. Now we'll just take the square root. So the square root of the gravitational constant times the mass over r will equal v. That is our second equation for analyzing a satellite. This is the speed of a satellite, which is related to the square root of the gravitational constant times the mass of, say, the Earth. If this were the satellite Sputnik, for example. And we're going to divide that by the radius or distance between them to get the speed. As the distance changes, the speed is going to change. Let's try a sample problem. In this example, a satellite orbits Earth 225 kilometers above its surface. Here's Earth. Here's a satellite 225 kilometers above its surface. And what's happening here is the satellite is going around. So we need to know the distance between them. We want to know maybe the speed and the time period it takes to make one full revolution. For A, let's find its orbital speed. We know that the speed is related to the square root of the gravitational constant times the mass that's generating the force that causes the circular motion of the satellite. Okay, it's not the mass of the satellite. Divided by the distance squared. Let's substitute. 6.67 e negative 11 times 5.97 E24 kilograms. That is the mass of the Earth, 5.97 E24 kilograms, divided by the distance between them. This is 225 kilometers. So we need to put that in meters, and it's above the surface. Very important to use those reading skills. So we need to take the radius of the Earth and add that 225,000 meters to it. 6.38 E6 plus 225,000 equals 6.605 E6. We're going to take the square root of all of that. We get 7,760 meters per second. 7,760 meters per second. So again, it's important to use those reading skills. So when it says above the surface, we have to take into account the distance from the center of Earth outwards. So that was the 6.38 E6 meters, plus the additional 225,000 meters from here to here, from the outer surface of the Earth to the satellite. All right, let's find the orbital speed of this satellite. Orbital period here. So t equals 2 pi times the square root of the distance between them so that was this number here that we added. And we have to cube that. Be careful in your calculations here. Divided by the gravitational constant and the mass that's being orbited, which is the mass of the Earth. Okay, so we're going to start with, I'm going to do it this way. I'm going to do 6.605 E6. And then I'm going to cube that, and I'm going to divide by, open parentheses, 6.67 E negative 11 times 5.97 E24, close parentheses. I'm going to take the square root of that number. So I'm basically taking the square root of 723,633. I get 2 pi times 850.67. So now we multiply by 2. and multiply by pi. And we get 5,345 seconds. The time period is in seconds. So if a question asks if you like to put it in minutes or hours or days, you'll have to convert that. So the time period is in seconds. All right, we're going to do one more thing. We're going to look at the gravitational field. The gravitational field on the surface of any object, it could be a softball or a baseball or the earth, it doesn't matter what the object is, but it equals the universal gravitational constant times the object's mass divided by the square of the distance from the object's center to maybe the surface or wherever the field is to be analyzed. Let's just do a simple problem here. Let's say we want to know the gravitational field on the surface of the Earth, like the average part of its surface, not at the top of a mountain, not at the bottom of the deepest trench in the ocean, but just the average surface. So we're going to take the gravitational field equals 6.67 E negative 11 times 5.97 E 24 kilograms. That's what we are using for the mass of the Earth. We got that from the previous problem. Divided by 6.38 E6 meters. So let's say that's at the surface where I want to find out what the gravitational field is. We have to square that. Crunch those numbers. You should get, guess what, 9.8 meters per second squared. Look familiar? So that is the acceleration of gravity on Earth. Now for the gravitational field, the unit is going to be in newtons per kilogram. That is newtons of force per kilogram of mass. And this should look pretty familiar to you because it looks like the Newton's universal law of gravitation, where we have force is the force of gravity, and then we just don't have a second mass here to analyze, so that mass went away. That's the only difference between this formula and Newton's universal gravitation law. All right. That concludes this lesson. Now you have a few different ways to analyze satellites and things that they orbit. Have a great day. Thanks for learning.